right, we are finally ready to move on to shapes of a distribution. They're looking at the lecture document. You'll see this on my screen, number 10. We're not ready for that for a few minutes. We're going to talk through what you see in this document for a little bit. So, shapes of a distribution. The shape of a distribution can be described in two ways, by its modality and its symmetry. Okay, let's talk about modality. And when you read that word, it might remind you of finding the mode, which is absolutely correct. The modality is, well, the number of modes. And so think of that, if you were to see maybe a histogram, those are going to be the bumps, if you will, in the distribution. So looking at those three examples just below, the first one in the upper left, you can see, well, we'd think of that as having just one bump in the center, one pronounced bump or peak to the data right there at the middle. So we would call that unimodal. The next one over to the right, that one has two peaks. One is just right of the center, and then another one about two bins over in that histogram. So the two bumps we would call bimodal, and it sort of tapers off, coming back down to the left. And even though there's a gap in the data there, we're still kind of thinking that as tapering down. We would not consider what's over in the far left in that first bin to be a bump, certainly not compared to the two big bumps. And then it sort of tapers over to the right as well. So bimodal. After bimodal, we usually just say something is multimodal. I suppose you could say trimodal if there were clearly three bumps, but just kind of what do we say in general. And so that last one there in the bottom center, multimodal, well, looks like to me it's sort of on the rise, and then we get one bump, and then it dips back down, and then another, and then it dips back down again, and then a third bump. There are several of those bins are seeing more data values than their neighbors. So multimodal makes sense there. Okay. You may remember the mode. What was the mode? The most frequently occurring data value. And so that has some significance in its own right, but really here, when you're talking about the shape of a distribution or just looking at a histogram, that's really where the modality is seen and probably has a better, more significant meaning. Okay, so there's the modality, and then next down is symmetry. A distribution can be symmetric, it can be skewed to the left, or it can be skewed to the right. And so we see an example of each of those. The one in the top center, we would call that symmetric. Now, does it mean it's perfectly symmetrical? Well, no. We're probably never going to get perfectly symmetrical. And so, but more or less, it's got kind of a mirror image. So it has its unimodal. This one happens to be unimodal, and then it tapers down to the left and tapers down to the right. And it doesn't taper down perfectly symmetrically, but well enough for us to call it symmetric as far as its shape. And then you look down, so the one on the lower left is skewed to the left, and in the lower right, skewed right. Now, as you're looking at those, why do we say that that's skewed left or skewed right? So if you look at the skewed left, all of the data, most of the data, I should say, is to the right side. So we call it skewed left because some of that data gets drug out to the left side, where you would think it, you wouldn't necessarily expect it to be looking at the rest of the data. So think of it as almost like centered at its mode or its unimodal peak, but then some of that data gets stretched out to the left. So it's skewed to the left. And the same with the picture, something similar with the picture on the right. So most of the data there is on the left side, but then some of that data gets stretched out in the right direction. So that's skewed to the right. Okay. Moving along. After we've talked about center, spread, and shape, it's time to talk about just other things that may occur with the distribution that would just sort of get categorized as other. So we call it unusual characteristics. Okay, let's see. Well, there could be an outlier, a data value that lies very far from the vast majority of the data set. So you may have heard of an outlier when it comes to statistics. That word probably gets used in day-to-day language every once in a blue moon. Oh, he's an outlier. Like he does something different than the rest of than the rest of the group. Maybe maybe that's kind of a stretch, but okay. So for example, we've got okay. So this is some data, and if you maximize that on your screen, you can see the numbers a little bit better because they're quite small. In that example, so I asked, it was that same class from 2 years ago, and I asked them how many hours per week about do they exercise? And so these are the results. So you see, we'd probably call this, unimodal, right? Most people were somewhere between 2.5 and 5 hours. And then quite a few people were somewhere between 5 and 7.5 hours. So somewhere between 2.5 and 7.5 hours, the majority of the class. But then some of them started, they said they worked out, more, even up to 10, up to 15 hours. And then one person was around 20 hours. And I believe that data value was exactly 20. So it gets put into that bin as you see. Well, they would be an outlier compared to the rest of the class. They were working out 20 hours or so per week on average, every week. Maybe they were into running or training for a marathon or who knows what they were doing, but they were definitely different than the rest of the group. And so we might very well consider them an outlier because they were very far from the rest of the data. Okay, and then if you look a little bit further down, so we've got the histogram right there at the top center. And below that, we've got two box plots. So what am I trying to highlight here? So if you're creating a histogram, it's really clear to see an outlier in a histogram because it's just going to be kind of its own thing, really far away from the other data points. But if you're creating a box plot, that's not the case. If you're creating a box plot, you would never know, just the nature of the way it's drawn, you would never know that there's an outlier in that data. So here are two box plots of that same data about the exercising so many hours per week. So you can see there on the left, we're just considering all of the data values as legitimate data values. We're not considering that one person who is at 20 hours to be anything different than anybody else. And actually looking at that box plot, it looks like they were a little bit above 20 hours. When you see that highest value, they were maybe at 21, even 22 hours maybe 21. Okay, so that's what your box plot would say if you just took all of the data and right in a box plot, we find the quartiles and stuff and we draw it. Okay. But if we did consider that person to be an outlier, what does that mean? What does it even mean to consider them to be an outlier versus not? Well, when you're making a box plot, you might say, you know what, I've got a good reason to kind of separate this one data value from the rest. So what you see there on the right is they did not consider that one person's their data when they constructed the box plot. They ignored it. Okay, so they created the box plot based on just the other numbers from the class. But even that said, you can't dismiss an outlier completely. You can't just pretend that somebody didn't answer that way. So we do note it, and we can see it with that tiny little dot right way out there at 21 hours. But it is not taken into consideration when we form the box plot. So when we're trying to find the median, right, we're not thinking of that number. We're just looking at the rest of the numbers and that sort of thing. Okay, looking a little bit further down, you see the 1.5 IQR criterion. What is this? Okay, this is a practice, and this is what number 10 is going to get to here in a second. This is a way to help figure out if a number is an outlier or not. We really don't want to introduce bias here. One person might say something's an outlier and feel like they have a good reason for that, and somebody else might look at the same data and say, no, this is not an outlier, and maybe have good reasons for that. So it'd be good if we had some sort of a protocol where we could crunch some numbers. So we call it the 1.5 IQR criterion. And this is what it says. A data value is suspected to be an outlier if it is 1.5 times the IQR below the first quartile, or 1.5 times the IQR above the third quartile. So we're going to practice that with this data set you see here, number 10. I want to note just what it says beneath there. It is the duty of the statistician to determine whether or not to include these data values as part of the sample or to remove them from the data set and consider them as outliers when they do the rest of their number crunching. So at the end of the day, a human does need to get involved. And so the 1.5 IQR criterion can be really, really helpful. But whether it passes or fails this criterion, it's up to the statistician to really look closely at the context of the situation and even the specifics of that outlier's data and why it was the way it was compared to the rest to determine that. So I would feel like, with the case with our person who was exercising so much more, in some contexts it might be reasonable to consider them an outlier, and in other contexts we might not want to do that. Maybe everybody's training for a marathon, right? And we'd say, well, everybody's training for a marathon, just most people, or supposedly just some people, are only training 1 hour a week for their marathon, while this person is training 21 hours a week for the marathon, and other people in between. Or we might say, you know what, most of the class there, maybe they enjoy working out, but there's a lot of other things they like to do, and so it's not they're doing it for recreation. But this person who's working out 21 hours, maybe that has to do with their job or their career. Maybe they are a lifeguard and they just have to be training and swimming, and maybe they're in the military, right? And that's just part of their life. It's not a choice in a sense. So maybe there you'd say really the lifestyles of these people are so different. We really want to consider them to be an outlier, where in other cases we might not. Okay, anyway, let's get to practice problem number 10 finally. Are there any suspected outliers in this data set? We will use the 1.5 IQR criterion. Notice we're not going to make the determination if it's an outlier. We're just going to find, are there any suspected outliers? And we're going to use that based on our criterion here. Okay, so I have the data set 5, 6, 12, 13, 15, 18, 22, 50. And just looking at those at a glance, any of those data values seem particularly far from the rest. You might say, yeah, 50, right? These all seem relatively close together, more or less, but then the jump here is really big. So we're kind of suspicious of 50 right from the start. But all right, let's do it crunching the numbers. So the first thing we need to do is figure out the IQR, right? Well, that's the difference between Q3 and Q1. So let's find Q2. Let's see, there are 8 data values there. 1, 2, 3, 4, 1, 2, 3, 4. So Q2 is right here, 14. Okay. Then looking down here, cut that in half. Q1 equals 9. And up here, cut that in half. Q3 equals 20. So this distance between Q1 and Q3, however far that is, that's the IQR. So here we have an IQR of 11. No big deal. No big deal. Okay. Now, the reason why we call it the 1.5 IQR criterion is because we're going to multiply that by 1.5. 1.5 times the IQR is what everybody agreed to long ago, and it hasn't changed. Well, 1.5 times 11 is 16.5. Okay, so what do we do with the 16.5? So if you read that criterion again, you'll notice it says, all right, any suspected outliers, we'll take this number and we'll subtract it from Q1. We'll think, are there any data values beyond 16.5 less than Q1? If there are, they're suspected outlier. Or if there are any data values above Q3 by 16.5. So we'll add the 16.5 to Q3. Are there any data values even further away than that? So let's take a look. Let's do the Q3 because we're really curious about that 50, right? So let's take Q3 and we're going to add 16.5. Well, so that'd be the 20 plus 16.5 is 36.5. So we went 1.5 IQR above Q3, and that brought us to 36.5. Well, 50 is even further out there. So 50 is a suspected outlier. It's way out beyond the rest of the data. We need to check it in the other direction as well. Let's take Q1 and subtract 16.5. Well, that'd be 9 minus 16.5, which is negative 7.5. Are there any data values even further back? Well, no, because the smallest data value is only 5. So we're well, this goes negative 7.5 is well beyond that already. There's nothing even further away. So nothing on the low end is suspected, but that 50 on the high end, yes, 50 is a suspected outlier. Okay. And then I make this note here. We kind of said this before, but if you're creating a box plot, just to reiterate this point, if 50 is decided to be an outlier, then remove this data point when creating a box plot. And I just wanted to highlight what that would look like if you did. So this might come up, maybe in your project, one of your long-term projects, especially. You might get some data and have a suspected outlier, and well, what do we do? So you would, if you do decide that it's an outlier, you would remove it from the data set. So notice we only have 5 up to 22. So we're thinking of the 50 as removed. Then we're going to calculate Q1, Q2, Q3 again. So at this point, with only 7 data values, 13 is Q2. And then if we want to find Q1 and Q3, you've got some choices. So as I said in the last video, I keep the 13 and look at these 4. And so I would draw Q1 right there. And I would keep the 13 and look at these 4. So I would draw Q3 right there. And then I would create my box plot. And so doing this by hand, okay, I'm going to go from 0 to 50. We are still going to put that in on our box plot, but it's going to be way out. Okay, so here it is. We're starting there at 5. The upper part is 22. And then we've got 9, 13, 16 and a half. So 9, we draw that. 13 is about right there. There's 15 about right in the middle. There's 13, 16 and a half. I'll draw my box. I'll draw these lines. But I'm also going to note 50 way out over here. And yeah, we can tell, oh yes, that is very far beyond the rest of the data, definitely. So it's still there in our graph. People can still see it. We're not trying to hide anything. But we're really drawing the attention here. This is our data. Okay, let's stop this video here. We will wrap it up in the next one.